Okay, so today we're going to be talking about rectangular approximation, okay, or estimating with finite sums. Um, it's the basis of the second part of calculus that we're going to be dealing with, okay, but we're going to start off slow. So here we go. Basically, we've been dealing with velocity and acceleration and position, okay, for a while. So let's consider an object moving at a constant rate of about 3 feet per second, okay? Since rate times time equals distance, or 3t equals d, if we draw a graph of this velocity, the distance the object travels is equal to the area under the curve, okay? So velocity we know is normally change in distance over change in time. So if we rewrite it to think of it as in terms of how to find distance, it's your rate times time. So this rectangle here represents a constant rate, right, of 3 feet per second. So this line up here, this one here, is your velocity. You're going this constant rate, okay? So every second, you're going 3 feet. So after 4 seconds, how far did you go? Well, if you plug it into your equation, 3 times 4 equals 12 feet. But also, if you notice, this area, when we graph the velocity as a constant velocity, this area underneath also represents that 12. This area, because we're talking about this rectangle with a height of 3 and a width of 4, so this total area is 12. Now this is something that they talk about in physics, whether you took AP Physics 1 or you took AP Physics C, they both talk about this idea of if you have the graph of velocity, the area underneath is representative of distance. Okay, so that's basically what we're talking about. But the problem is that this only works when we have this kind of linear or easily found area. What happens when the velocity is not constant, okay? So the distance will still be the area under that curve, but what about something like this? If my velocity is changing over time. So this becomes problematic because if this is my velocity and I go to make some kind of rectangle, if I make a rectangle that's this high and like this, then I'm missing all of this, right? Or if I make my rectangle like this, I have all of this extra, so that's not very accurate. So what can we do? So there's this method that we're going to be talking about today, rectangular approximation. So instead of using one rectangle, we're actually going to create a bunch of smaller rectangles. So we could estimate the area under this curve by drawing rectangles, and we're going to have them touch at their left corners. So we're going to actually create many rectangles. Okay, this is called the left-hand rectangular approximation method, or LRAM, and also known as Riemann or Riemann sums in some textbooks. Okay, so basically what I'm going to do is I'm going to use 4 different rectangles. Okay, so here we go. I'm going to create these rectangles based on my function. So they're going to touch on the left side. So the left side, we're going to start here at 0. When I plug 0 into my function, it gives me 1, because 0 squared is 0, 1/8 times 0 is 0, 0 plus 1 is 1. So this area of this rectangle is 1. And see how it touches right here on this left side? So this height is given by my function. This is f of 0, and this is at 0. Okay? All right. So let's look at the next one. The next one that I'm going to create is going to be 1. So basically we're talking about this height here. What's this height from here to here? What's f of 1? Okay, so I plug 1 into my equation, and I get 1 1/8. So the area for that rectangle is 1 1/8, because the width is 1, the height is 1 1/8. Next, I'm going to do it for 2, and I get 1 1/2. So there's that rectangle. And then I do it for 3, and I get 2 1/8. Okay? So what I've done is I've approximated the area under the curve using these 4 rectangles. Now, I realized that we're missing a bunch of area, okay, and we'll talk about that in a minute. But this will give me a pretty good approximation of what the minimum value could be. So when I add all of those up, I get 5.75 for the area underneath there. Now, I know this is an under approximation because I'm missing a ton of area. I mean, if you look at it, you're missing this part here and all of this and all of this and all of this. So I know my number's got to be bigger than this. But there are times when we approximate and we need to know kind of like a minimum, okay? So this is called LRAM, or left-handed rectangular approximation method, because I use the rectangles hitting on their left side. Well, if there is a LRAM, then obviously there is also what we call RRAM, okay? So we could also use the right-hand rectangular approximation method, or RRAM. And basically it's the same idea, except my rectangles hit on the right side, okay? And again, same process here. I plug my left-handed values. So on the last one I use 0, 1, 2, and 3, but on this one I'm using 1, 2, 3, and 4. These values, these heights, from here to here, and from here to here, and from here to here, okay? So for this one, my values come from the right-hand side. Now, since I broke this up into 4 equal pieces, my width on all of these is 1, and like the height here is that 1 1/8, and this height is 1.5. Okay, but the widths are all 1. Okay, so when we add those up, we get our approximation of 7.75. Now, just like the last one was an under approximation, this one here is an over approximation. Okay, because I have extra area. Those rectangles are above my curve. So again, this right here, this right here, this right here, this right here, and this right here, that's extra. So we know basically that our actual answer should be less than 7.75, but greater than the 5.75. Okay? So what do you think is coming next? If we had left hand and then it's an under approximation, and we have a right hand, which is an over approximation, there's also another method that we can use called MRAM, which is the midpoint rectangular approximation method. So instead of my rectangle hitting on the left or the right side, it hits the function right in the middle. Now this tends to be a little bit more difficult because if we're hitting between 0 and 1, we're actually going to be hitting that rectangle at 1/2. Okay, so we start getting a little bit more difficult. So here's my table. So my first point I'm picking is going to be 1/2. So right here at 1/2. So the height of my rectangle is going to be right here in the middle. And then here at 0.7, 0.5, 1.5, here at 2.5, and this one at 3.5. Okay, so basically my rectangles, the heights are coming from the middle. So I plug it into my equation, and this is where calculators will come in handy. So when I plug it into my actual velocity equation, so 1/2 squared times 1/8 plus 1, that's my heights. Okay. So here we go. And you can see, like I said, how these rectangles hit in the middle. Okay. So this, you can see, will give us a better approximation because basically this little piece here and this little piece here, they almost fill each other in. So like this little piece right here almost fills in that piece right there. So this is definitely going to give me a much better approximation. And when I do this, the approximate area is 6.625, which is definitely between my 5 and 7 that I got. And you'll be glad to know, okay, that the actual area is really close to that. Well, how do we get a better approximation? So LRAM and RRAM are out. MRAM's the best of the three, but what could give me a better approximation? approximation? Well, I could use more rectangles. So instead of just using 4 rectangles, I'm going to split them into 8 rectangles. Okay, so I'm going to use 8 subintervals. So basically between 0 and 1, I'm going to have 2 rectangles. So I'm going to take 0, 1, I'm going to split it up, and I'm going to have 2 rectangles here instead of 1, and that cuts down on how much over and under I have. And I'm going to use MRAM because that's the best approximation I have. Okay, so real quickly, again, I'm just going to be plugging these in using the calculator to do it for me. So my first rectangle, and again, since this is 0.5 and I'm using MRAM, that means the middle of my rectangle is at 0.25. And then this one is going to be at 0.75. And then again, this one right here is going to be at 1.25. Okay, so these numbers are going to get kind of hairy. All right, so here we go. So first 0.25, plug it into my function. I get that. Then I use 0.75, and basically I get all of these. All right. Now, these are all my heights. Okay. Now, on the last 3 examples, all of my widths were 1. So any of my heights times the width gave me the same value. But here, it's now different because these are my heights, right? But what is the width? So the height of this rectangle from here to here is 1.00781. But what is the width from here to here? It's no longer 1, it's 0.5. So what is my actual area in here? Well, that would be this times this. Okay? But instead of actually multiplying each height by the width, and since all of these are the same, what I can do is to shortcut this a little bit, is I add up all my heights and then multiply it by the width of each one. Okay? So basically that would be like, instead of doing this, the area total equaling the length of 1 times 0.5 plus the length of the second one times 0.5 plus the length of the third one times 0.5, the width. Basically what we've done is we've taken, since they all have a factor of 0.5, we've done L1 plus L2 plus L3 plus dot 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 dot, added up all of the lengths and then multiplied by the width to get the area. Okay, so that's basically what I did there. And then when I do that, I get my total area, which is 6.6 as my approximate area. Okay? Now, the exact answer, so if I actually had a calculator or a computer do this and made my rectangles even smaller and smaller and smaller, you would find that the exact answer for this problem is 6.6 repeating, or 6 2/3. Okay? So you could see that doing this, although it's just an approximation, that approximation is pretty close. Now, the problem with doing rectangular approximation like this is that it takes a long time. And we are only doing from, say, 0 to 4 seconds. And most velocity problems that you're dealing with go much farther beyond that. So it's not very practical to do it by hand every single time. But we'll get to the other part later. Okay? All right, so a couple things that you have to remember. Some probably terminology that you don't know. Inscribed rectangles are when we talk about rectangles that are below the curve. When you talk about something inscribed, we're talking about inside of something. So, for instance, inscribed rectangles look like this. Notice that all of the rectangle is below the curve. Okay, that's because they are inscribed. So there's a mixture, and you can see that we're using a mixture of both left-hand approximation here, and on this side it's right-hand approximation, and this one looks like it hits on both sides. Okay, so when we talk about something being inscribed, we're talking about inside or below the curve, versus circumscribed rectangles, and it's circumscribed, not the other word. they are all above the curve. So notice both corners hit, or both corners are above or on the curve. Okay, all of them. There's no missing area. So inscribed rectangles tend to be an under approximation, where circumscribed rectangles are all above the curve. Okay, do you see the difference? And this is just terminology that you guys need to know before we move on. Okay, but that's basically how rectangular approximation works. They'll give you the type of rectangles you're using, whether it be left hand, right hand, or midpoint. We'll also at a later date talk about trapezoidal approximation, but that's for another time. All right. Now, we will be learning how to find exact area under the curve if we have the equation, but rectangular approximation methods are still useful for finding area under the curve if we don't have an equation. So when we're talking about real-world data that doesn't fit an exact curve, rectangular approximation works really well when you're talking about statistical data or sales data, things like that. Calculators can do these rectangular approximation problems, but since it's a limited usefulness, we're going to be learning better methods. You could use the calculator to kind of check your work, and most of the calculators actually do a rectangular approximation method, but the rectangles are so small it would be almost impossible for a person to actually do them. Okay, but we will eventually do it using a calculator, and you'll see what we're doing. Okay, and that's rectangular approximation.